If you've already had some experience in playing around with Vertex shaders but you'd still like some clarification, or even if you're a complete beginner wanting to see an intuitive overview of the stages involved during Vertex data processing, then this tutorial is for you. I've split the video up into 3 chapters. We'll start by taking a quick look at what it means to create and export 3D models, then how to organise that model data within our main program on the CPU side, and then how to process Vertex data inside the Vertex shader. So let's start by considering what a vertex actually is. Any object in reality can be represented by points, and a vertex is basically just a point in space. For example, beginner tutorials, including my own, typically show you something like a cube being drawn by using coordinates that we've typed in manually into an array, but you can't carry on like that once you start drawing proper 3D models, which is why we use 3D modelling software such as Blender. There are loads of different ways to manipulate vertex positions in modelling software. Imagine trying to enter these values into an array manually and then having to update them every time you want to update the model. It'd be a nightmare. To apply images to the mesh faces, we first select an image and then we control how the image texture coordinates map onto the faces by adjusting the UV map. Now, whenever we want to draw models in computer graphics, we need to load all of the model's X, Y and Z values into our program. And so once we're happy with the model inside the modelling software, we then need to export all of its vertices and texture coordinates by selecting one of several standard file formats. For example, when using OpenGL, as I am for this tutorial, I've always exported my models by selecting the wavefront option, which produces an object file and a material file. As an example, if we start with a cube that has a total width and height of 4 units, and then export it as an object file, we can see that the vertex position values are all +2 or -2, but we don't yet have any texture coordinates. And also notice that the associated material file, which is called a companion file, doesn't yet contain any details. Now let's create a UV map for just one of the faces of the cube and apply an image to that face, but we also need to reverse the texture coordinates in both directions because the image is displaying as flipped from left to right and top to bottom. When we re-export the cube and take another look at the object file, we can see that it now lists texture coordinates ranging from 0 to 1 and that the material file now lists the name of the image. The bottom left of an image corresponds to texture coordinates 0, 0 and the top right of an image corresponds to texture coordinates 1, 1. The UV map corresponds to the entire cube face, and so as I now reduce its width to roughly half the width of the image, you can see how the image stretches across the face of the cube. Also notice that the object file and the material file are both just text files, which is why we can read them by using a text editor. So imagine if we could store all that data into different lists. We could then loop through each list and access each value at the given position. The programming language C++ allows us to store data inside arrays, lists and vectors, which in a more general manner we can just think of as being lists of data. The process of reading data files and then organising it into storage is known as parsing, but instead of parsing the files ourselves, we can use a model import library such as a simp. After the data has been imported by a simp, it looks like this. We've got the vertices, the normal vectors, the texture coordinates and the index values. Just before we dive into looking at how vertex shader processing works, we need to first pass the vertices, the normal vectors and the texture coordinates as arguments to OpenGL in the form of array buffers and the index values in the form of an element array buffer. We use an image loader to load the model's images into memory, which we then bind individually immediately before the draw call for the given mesh, but that isn't really relevant to vertex shader processing, and so we'll look at how images and normal vectors are processed inside the fragment shader in the next tutorial. So now we're ready to look at how we process vertex data inside the vertex shader. Remember how a simp provides the imported data to us on the CPU side, organised into separate streams? Well, we've essentially just passed that same data to the vertex shader in the same manner. Although notice how the index values are not being fed into the vertex shader, and that's because those index values that we just stored in an element array buffer on the CPU side are now being used by OpenGL to select the correct vertex to be fed into these vertex input attributes. Now, you might have heard the term shader invocation, which I tend to think of as an iteration because it essentially just means a single execution of the particular shader stage. Each invocation of the vertex shader processes only a single vertex, and in contrast to programming on the CPU side, which retains the modified state of variables as we update their values during the main loop, the modified state of a shader's global variables is not retained from one invocation to the next. This limitation means that we cannot manipulate the values of the vertex currently being processed based on the values or transformed values of vertices already processed in previous invocations. We'll look at what uniform variables are in just a moment, but let's first produce some transformations. So let's start by rotating a model's vertices in 3D space around a single axis, which only requires these two lines of trigonometry, which are nothing more than right-angled triangles that we learn in college, which looks like this. Scaling a model is really easy because we just need to multiply the x, y and z position values by a value larger than 1 to make it bigger or less than 1 to make it smaller, so we can scale all three axes, or just the x-axis to stretch it wider, or just the y-axis to stretch it taller, or just the z-axis to stretch it into and out of the screen. To combine rotations with scaling, we just use the rotated position values that we just calculated as the input values for the scaling. Moving a model is also really easy because we just add or subtract values to or from its x, y and z values. So coming back to uniform variables, uniforms are a special type of global shader variable that we can pass values to from the CPU side. Ordinary global shader variables have fixed values during runtime because they are set when the shader text file is read and compiled whenever you run your program, whereas we can update a uniform's value dynamically during runtime on the CPU side before making the draw call. That's what I'm doing here. I'm continuously increasing the value of counter on the CPU side and then passing it to the Vertex shader, otherwise there'd be no way for me to produce continuous transformations. In contrast to creating the transformations ourselves directly inside the Vertex shader as we've just done, we could instead use transformation matrices from the GLM maths library for example, and although the matrices just contain the transformations you just saw in action, we can multiply them together to produce a combined transformation stored as a single matrix, which is a big advantage. Now to pass a uniform value to the shader from the CPU side, we just need to call the appropriate GLUniform function and pass the uniform location and value as arguments. Libraries such as GLM also provide us with something called a view matrix, which rotates and translates all the vertex positions of all the models in 3D space, such that it's as if we've moved and rotated the camera to the corresponding viewpoint, but really it's the vertices that are being moved and rotated because there's no such thing as a camera unless you decide to render one. Now, just before OpenGL assembles all of our points into triangles, there is one more very important concept that we should at least be aware of, even though we don't really need to understand it in great depth, and that is the projection matrix. So now that we've finished transforming all of our model's vertices within 3D space, we need to project those points onto a 2D flat surface. Consider a photograph, which is just a 2D representation of 3D reality. That works because the light rays that are travelling at various angles through 3D space pass through the camera lens onto a 2D surface, which is the camera sensor. Computer graphics works in the same way in that we project positions in 3D space onto our 2D display window, which is also called the near plane of the view frustum. Now I want you to keep in mind that everything you're about to see, although it's based on the y-axis, also applies exactly the same for the x-axis. All we need is a single triangle which we extend to produce a second triangle, and so the ratio of the lengths of the sides for both triangles is the same, which means the ratio of this side divided by this side is equal to the ratio of this side divided by this side, which is simply just the slope of the hypotenuse, and so the triangles are proportional to each other. Also notice that I haven't drawn the far plane, which is because it's only the near plane that affects the field of view calculation. By studying the diagram, we can see that the position of y1 along the slope of the frustum boundary is simply the ratio of the slope multiplied by the near plane distance along the z-axis. The resulting values, as projected onto the near plane, are also scaled to be in the so-called normalised device coordinates range of -1 to +1, as required by the graphics pipeline. But we now have two problems that we need to deal with. The first is that we don't want to rasterise any points that lie outside of the view frustum, and the second is that we have a potential divide by zero issue. We know that our extended triangle's ratio is y over z, which means we are dividing by zero if the z value of any given point in 3D space is 0. And so this is where an opportunity presents itself to us, and that is to clip away all the points that lie outside of the view frustum before dividing by z, and for that we need clip space. The best explanation I could come up with is to start by setting the y and z values of the triangles to 1 and 2 and the angle to 45 degrees, as you can see on screen now, just to keep the numbers as simple as possible, and also notice how y1 and y2 both lie at the boundary of the frustum. The way 3D space is transformed to clip space is that we just don't do the divide by z part, and so clip space for y is just the y value multiplied by the near plane distance along the z axis. Because we need to use the value of z in the division of the projection calculation, and that z is also going to be scaled to the range -1 to +1, which happens later on independently of the x and y projection that we're doing now, and so I'll cover that aspect in a later tutorial, we therefore need to make a copy of z, which by convention we store as w, and then w together with x, y and z is called a homogeneous coordinate. But the key question to ask ourselves is, why does that actually make any sense geometrically? Let's now reduce the angle from 45 degrees to 22.5 degrees, and so for our point to remain at the boundary we need to change its position. If we move it along only the y-axis, it needs to be at 0.83, or if we move it along only the z-axis, it needs to be at 4.82, which we can calculate from adjacent equals 1.17 divided by 0.414 equals 2.82 plus 2 equals 4.82. Let's split this illustration up into 3 separate triangles to help us see what's happening a little bit more clearly. By scaling the height of the near plane from 0.414 to 1, we've also increased the near plane axis distance to 2.41, which by the way is also known as the focal length. But to keep the geometry valid, we must scale the entire length of the z-axis, not just the focal length. When we multiply the point's y value of 2 by the focal length of 2.41, we can see that we also get 4.82, just like we did when we calculated it this way. This is how the frustum looks to begin with, this is how it looks after reducing the field of view to 22.5 degrees, and then this is how it looks after scaling it to normalised device coordinates. As another example, we have points in 3D space along the full length of the z-axis where y equals 1, and all of those points, including this one, map to y clip 2.41 just here, but once again as a z value. And so the reason this all seems so perplexing is because by multiplying the x or y value of any given point in 3D space by the scaled focal length, the resulting clipping value for the point is a z value, not an x or a y value, which is the reason why w is set to be a copy of the given point's z value in 3D space. Also notice that for the 45 degrees field of view and the near plane height of 1 that we started off with, the resulting x clip and y clip values for any given point are equal to its positional values in 3D space, which is simply because at 45 degrees the height of the near plane and the focal length are equal to each other, which in this case is 1, and therefore by multiplying the positional values in 3D space by 1 to get clip space, the values remain the same.